Okay, so in the previous video, we went over change of variables. If you haven't watched that video, first watch that video. I'm wearing the same thing. You'll recognize the video very easily. So in that video, we translated this dx integral into a du integral, okay? This did not take trig substitution. As you can see, there's no theta. It's just a different variable. And we saw that the area that this is a definite integral. So they were asking us to calculate area under this curve. And by the way, you can always write this like so. This integral equals this integral, okay? Because the area under original curve from 1 to 5 is the exact same area as this translated curve from 1 to 3 and then multiplied by a constant 1/2, okay? So geometrically, those two areas equal one another. The same thing happens, the exactly same thing happens when you are translating a dx integral into a d theta integral. Different from du integral, here you need to use a triangle to make that jump, make that translation. So instead of going to du, you're going to d theta. But everything else is the same. And yes, you can write the equal sign between these two integrals. And yes, area that is under this curve from square root of 3 to 2 will be the same area here with the new bounds and some new function, which will be a function of theta, okay? So first, let me outline what we're doing, okay? With these sorts of integrals, I do an extra step, which I never do otherwise. Here it does make sense to do this, okay? So this is the original integral that was given to me. I just outline these things. This is kind of what I'm doing, okay? I need this in terms of theta. I need this in terms of theta, this, and then I also have x upper limit. I need theta upper limit, and then x lower limit will give me theta lower limit, okay? So this is kind of a game plan of what we're really doing. As I mentioned, this is a trig substitution, so obviously you're gonna need a triangle. And for the purposes of determining sides of the triangle, you only need to look at this part of this integral, okay? Just what is under the square root. And here's why. Because what you have under the square root is something squared minus something else squared, okay? And that looks like Pythagorean theorem. So this is a hypotenuse squared and one of the other side one squared, okay? So then you rewrite this as x squared minus square root of 3 squared, which it will give you 3. So don't think that this is one of the sides is 3. No, if this was 9, one of the sides would be 3. If that's 3, then one of the sides is square root of 3, okay? So you already know that this has to be the hypotenuse because you never subtract one of the sides from either of the sides, only from the hypotenuse you subtract, okay? So that, you see a minus sign, that whatever comes before that has to be the hypotenuse. So x is definitively hypotenuse here. So this vertical side is this whole expression, and then the base of this triangle is square root of 3, again, not 3, square root of 3. So since you have the correctly labeled sides of the triangle, then that is kind of 50% of the solution right there. Because after this, the only thing I'm going to do is look at the different ratios, which are trig functions, right? So there are 6 possible ratios of 3 sides of the triangle, and then there are 6 trigonometric functions, right? So I choose wisely though. So what I need to express is this and that, right? So which is opposite. By the way, this is theta, and that's really important because trig functions are features of angles, not of triangles. It's angle is really the key here. So opposite of that, so this is the opposite side. This is the hypotenuse, and this is the adjacent. And to who? To theta. So I want to connect this to a number. I definitely don't want to connect an x expression to another x because I'm trying to get rid of x. I'm trying to write everything in terms of theta. So I look here and I find that opposite side is involved with 4 different ratios, but I want it to be connected to the adjacent, and I also want it to be at the top. So this is the one that I'm going to use, okay? And I'm going to express x squared minus 3 equals to 3 times tangent theta, so that I have that ready. So then in my new integral, I'm going to substitute that term with this term. And notice that the right side of this equation doesn't have any x's. It only has theta and some number, okay? And that's exactly what you want to do. And with the same logic, I'm going to choose a ratio that has hypotenuse connected to the number, which is the base or the adjacent side. So that's the one. And I also want hypotenuse to be at the top. I could go with that, but then I have to flip it. So this is the perfect ratio to choose. So I'm going to get that. So the trig functions are like a bridge. As you can see, even visually, it looks like a bridge here, you see, that connects something that is always true. Tangent always equals opposite over adjacent. Secant always equals hypotenuse over adjacent. But in our case, in our specific case, it equals x over square root of 3 secant, and then tangent was this expression. Okay, so now I'm going to express x, which is square root of 3 times secant theta. Okay, so these two, I've got those. So now I'm going to get dx, which you get from taking derivative of both sides, differentiate both sides. So the left side is dx and the right side is square root of 3, and derivative of secant is secant theta tangent theta. And then don't forget d theta, okay? At this point, you have all 3 of the components that you had in the integral. But we're not done yet because we need new bounds, new limits of integration. So those were x limits of integration. You know that because you had initially dx integral. So these must have been x bounds. So now I'm going to get theta bounds. And how am I going to do that? Do I have an expression that connects x with theta? I do, right here. So that I can make x from thetas or theta from x's, okay? So x over square root of 3 equals secant theta. So you can express theta as arcsecant of x over square root of 3, or you can simply leave it as it is and then put upper bound here, which is 2, and then this would give you upper bound theta, and then ask the following question. Secant of what angle will give you 2 over square root of 3? And the answer to that is secant of 30 degrees, which is same as pi over 6. Okay, so secant pi over 6. With the same logic, and here you put x upper bound to get theta upper bound. These get canceled. This is 1. Same question. Secant of what angle gives you 1? Okay, if you're not familiar with secants, then think about cosine, because secant is 1 over cosine. Okay, so cosine is 1 when angle is 0. So then I'll pick that one. So that should be secant 0. Okay, so then this is theta upper bound, and this is theta lower bound. So my new interval goes from 0 to pi over 6. Then I'm going to get expression for whatever I had in the numerator. So that thing, okay, instead of this. Then that divided by x, or times, so x expression is this, and then dx is this whole thing. Okay, so things will get canceled. One of the Square root of 3's get canceled. Secant theta and secant theta get canceled. But what I'm left with is tangent square theta d theta, okay? And then square root of 3 will come out of the integral. Since we don't know antiderivative of tangent square theta, you can substitute tangent square theta with its trig identity, which tangent square theta equals secant square theta minus 1. And we can take antiderivative or integral of secant square theta. That's simply tangent theta, because derivative of tangent is secant square. Okay, so square root of 3 tangent theta minus theta. All of that from... The reason why we got new bounds is that you don't have to go back to x, because if you did, you would have to change this with this expression, and then theta with this expression right here. You would say theta equals arc secant x over square root of 3, and then x going back to x bounds, right? So you would get the same exact answer, but it's just a bit more difficult to do it that way than getting the new bounds and never going back to x. Okay, so I'm going to apply a fundamental theorem of calculus, take the difference of upper bound and lower bound. Tangent of pi over 6 minus pi over 6, and tangent of 0, which is 0, minus 0. Okay, so this term is 0, so you don't need that. Then you have square root of 3 times, so tangent of pi over 6, this is same as sine of 30 degrees over cosine of 30 degrees, okay? So that is simply 1 over square root of 3, and that is just pi over 6. You pop that in your calculator, you're gonna get, you can box that, and then that's the final answer, okay? So the reason why this is super useful is because you're effectively calculating an easier integral, same area, but this is easier to integrate. So this is the reason why you moved from this, initially from this integral to this integral. In trig substitution, you do the exact same thing, but the jump from dx integral to d theta integral involves using the triangle. The reason why is because you recognize that these could represent sides of the triangle, because there's something squared and something else squared, and the difference of those, that's Pythagorean theorem, and you correctly recognize that you need a triangle. If you didn't have this going on here, if you had an equation of a circle going on here, you couldn't use a triangle to do this type of a trig substitution. So only reason you can do this is because formula of a right triangle sitting there.